we've done a lot of work over the years on controls, right? And we have all these things that we're controlling. Some of it's electrical, some of it's mechanical. All the controls involve a lot of different types of electrical formats, right? We have low voltage, high voltage, amps, resistance, things like that. So for our students to work with this, they need to have a basic understanding of electricity. So we thought we'd put together a PowerPoint little presentation on some fundamentals of electricity and how it relates to measurement and verification. So we're going to go through some slides on that, talk about it a little bit, and give you a little bit of background. And it's going to seem pretty basic, I think, to a couple people here, and maybe some people, it might be some new information. But we want to provide this background as a way to start getting into the afternoon activities. And just as a backdrop of what I've done relative to this over the years, I had a project that kind of directly relates to this when I was doing my consulting engineering, which I still do. It was a project with a utility looking at demand-side management, and we were trying to evaluate whether demand control remotely by the utility to drop out air conditioning would have a significant enough impact to validate them going to a utility rate to do so. So I had to go up on, 20, 30 different building rooftops over a course of 4 years, install demand, temperature, relative humidity loggers on anywhere from 3 or 4 rooftops to about 10 rooftops on a building, and did this over a period of 4 years, collecting data and putting it together. So when I did that, I found out some things for me on a measuring perspective that I'll talk about a little bit later, but gave me some insight into what to do. However, I did this back in the aughts, so it's 2004 or 2007. And oddly enough, technology changes, right? So some of the things I learned back then about what I would suggest people to do for metering versus today are going to be very much different. And that'll play in, and you'll probably hear some of this when Mary comes up to talk, because her and I talked a little bit about that yesterday from a perspective of the complexity of doing this. It's not as bad as it used to be, but there are some meters out there that still have really complex methods of having to install them, so you got to be careful about that. So fundamentals of measuring electrical power and building operations. I'm going to start from a very basic level here of talking about electrons flowing. And then we'll get into DC, AC, electrical, Ohm's law, very important, especially when you're talking about using 420 milliamps. One thing that we have not covered, at least to Brian and mine's recollection during any of these institutes, is the triangle, the electrical triangle. So we'll cover that, and we'll talk about common electrical for controls. And by the way, I'm not a know-it-all, so there may be some things that we can add to this that you know. So let's do that too during the course of the presentation. And then we'll talk about monitoring electrical. So one site I've found very helpful for my students is to go to a YouTube site called The Engineering Mindset. Has anybody used that at all? You guys find it useful? And it's, in some cases, it's a little more detailed than my students really want to get into, but in a lot of cases, it's very informative for them. So I put that up there, and you can go into it. They actually touch on some of the things that I'm going to talk about here. So electrons. Electricity is electrons flowing, right? So basically, if you excite the electrons of an atom to a big enough or high enough level, they're going to be willing to get away from that atom. And then they can flow. And that's how we get electricity. So one of the things I like to do when I'm talking with my students is to talk about sustainability. And so this gives me an opportunity to show an atom. And what atoms do I have up there? Carbon atoms, right? So here I have carbon 12, 13, and 14. This is one of the things that we talk about in sustainability and climate change and global warming that point to the science that says it's us it's burning fossil fuels that's creating this issue. And so I would take some time to step through it, and I'll give you a quick rundown on it. Carbon-12, that's things that have been dead for a long time, fossil fuels. Carbon-13, it's a pretty stable thing, just as stable as carbon-12, but you don't see it coming from too much other than things like volcanoes. So it's a pretty consistent number out there. Carbon-14, it's unstable. It's the isotope of carbon that decays over time. Somewhere over 5,000 years it gets a half-life, right? So that's the one that we watched that tells us how much of the carbon is something that's least recently living. Because a plant recently died, it's going to have carbon-14 in it, and we can date it based on that level, right? So we look at the atmosphere, and we can tell by the makeup of the CO2 what carbon atoms they have, and that'll tell us where that carbon's coming from. You look at the data today compared to past data, and it clearly shows that a higher and higher percentage is going to carbon-12, which means dead things giving up carbon into the atmosphere, burning fossil fuels. Voila, there we go. There's a good website to go to that it's in the notes of this, I think, and you can just you can download these notes. I have it online. I sent out a link to everybody today, so you can get it right off your Google Drive. These slides are up there. Some other information I put up there, and we'll talk a little bit more about that over time. But it's also a site where everybody can contribute by putting up information to share with everybody else up there. We're going to be setting up different directories or file folders in there to hopefully make it more useful over time. But this is our starting point to do that. Because you're here, you're going to have access to it. We're going to be establishing guidelines, so your access won't be unlimited time frame. We're going to review who's there and whether you've been involved and things like that to see who has access, who doesn't have access. We just haven't feathered through all that yet. So we'll be doing that over time. So electrons flowing, electricity. So I guess I just talked through this, but when you have a electrical generation, you're basically releasing those electrons that go through the wires. They're trying to find their path of least resistance, and they end up getting back to the source, back to the generation site, and then they just get moved around again. It's like pumping it through the system. There's a website there, and it talks about why you never really quite run out of electrons on a system like that. This is from DOE, the picture. But when you move a magnet through a coil of wire, it also has a way of generating electricity by stripping electrons. And that's how we generate it back at the plant. It's that pumping action, right? This website takes you to a number of different methods to generate electricity, and it goes through the steps, very basic, but it gives everybody an idea of, at least for our students, of how electricity can be generated. So electrical generation in the States, we've already kind of talked about this today. Fossil fuels, 60-some% of electrical generating energy in the United States. I know in Wisconsin it's like about 67%. We have about 46% coal, and the rest between 67 and 46, so it's 30% is natural gas, and that percentage is getting bigger and bigger. We have United States almost 17% renewable, and there's other sources, 0.3, so that'd be like, nuclear is almost 20%, and then there's other sources. So the website for that is EIA, it's a government website, and you go there and get a lot more information. So hopefully, during this presentation, you're going to get a lot of different resources to go to look up information. And you'll see that peppered throughout these slides. And again, it's available to you on the Google Drive. If you have questions about the Google Drive, by the way, just pull me aside some point, and I'll show you how to get there, okay? So electrons flowing, voltage, it's electrical potential. So the greater the voltage, the stronger the pushing power for those electrons. It's kind of like the pressure in a garden hose. The higher the pressure in a garden hose, the faster that water is going to move, right? We, for nomenclature, use either E or V. It's a driving force. Amperage is the flow of electrons. So voltage is what's giving it that potential to move. Amperage is the actual flow of electrons. Amperage, we typically call it I or A. And it's the water flowing through the garden hose. There's two types of electricity we use, DC and AC. So everything coming out of our sockets is AC. Items that we use, like most of the things that we have at our desktops right now, are all DC. Cameras, DC. Rechargeable batteries, DC. So, another sustainability thing. Who here uses rechargeable batteries on a regular basis? I mean, at our schools, it's kind of hard to do, isn't it? But if you look at the economics of it, at worst, the cost of rechargeable batteries breaks even with buying regular batteries, at worst. It's just a matter of getting used to making sure things are charged and all that sort of stuff. It's a kind of a hassle. Don's nodding his head because he's aware of that, right?
Recharging right now.
Recharging right now, all right. So, all right, so DC, it's a constant. We just have a constant line of voltage or amperage. It doesn't vary. AC, it varies. Well, I guess I got to go through some equations first. DC power, when we calculate the wattage need for something, we just take amps times volts. That's our wattage. Pretty simple equation. For a car, wattage is equivalent to power, which would be horsepower. What's under your hood? Energy is how long you're using that wattage. You're using over a certain period of time. That takes energy to do that. So when you look at trying to figure out, okay, I'm looking at my electric bill, how do I calculate how much energy I used? Well, you look at your demand, your time. So time times wattage gives you watt hours, or divide by 1,000, you get kilowatt hours. And so there's these basic equations that we need to have our students start using. And in my classes, what I try to do is give these basic equations to them and go through sample exercises on a regular basis so that by the end of the semester, they have this down. Well, I hope. It does vary. So alternating current, instead of being a constant line, it's constantly going from plus to minus. And it's over time, right? And that time is, they think about it in terms of degrees. But it goes through the cycle of from 0, max, back through 0 again, min, back and forth, back and forth. How often it does that, how often it goes between positive and negative is hertz. So we let our students know that, and we let them know that in the United States, that common number is 60 hertz. In Europe, it'll be 50 hertz. Our frequency drives, they vary that all over the board, right? Depending on what we need. So I like to show them a little bit about, okay, here we have, in this case, our volts or amperage, just showing them this is how it looks. They can clearly see what the cycle is from 0 to 360 degrees and on. And this is clearly showing that it's crossing 0. They both cross 0 at the same time. And that's really important for them to understand that in a purely resistive circuit, amperage and voltage cross 0 at the same time. So calculating power for this, it's watts is equal to amps times volts times power factor. This gets us into that discussion about power factor and leads us into the power triangle that we're going to be talking about. So for power factor, you have to come up with what that is. And the power factor is actually the relationship between the energy that does what you want, the work that you want, compared to the total power being used. And the total power includes a little bit of something other than pure resistive loads, inductive or capacitance type of loads. So there's this reactive component to it. So power factor accounts for that. So our energy is the same calculation. Kilowatt hours is equal to kW times hours of use. But determining the wattage and therefore kW is different. And of course, you saw in the previous slide that kW is watts divided by 1,000. So you got to make sure you drive that home to them all the time for at least a semester so they get that. That gets us into Ohm's law. So for Ohm's law, V equals IR. Something that's very important for them as a control tech when you're teaching that curriculum to know. And we use this, and Brian, you're going to be using that this afternoon, right?
Yeah, a little bit.
A little bit?
Yeah.
Okay. So in Ohm's law, you basically cover up any one of these and determine what the other one is. You have to have two, no two of them, you can calculate the third one. Pretty straightforward. So on a 420 milliamp circuit, you can calculate, if you know the resistors in there, you can calculate the voltage drop across any resistor. So it's a very handy tool to have. This website here, I just Googled this website. I didn't Google the website itself. I just Googled information on trying to figure out with Ohm's law what the voltage drops were. And this website came up. It happens to be Southwest Technical College in beautiful Wisconsin, Prairie du Chien, Wisconsin. So just had to throw that plug in there. Actually, it's Fairmont, Wisconsin. My sister-in-law is from there. But anyway, so they have a lot of good information there, very basic, but they give you some calculations. Your students some calculations to go through. They have both electrical and some HVAC stuff, so you might want to check out something like that. Those are the type of resources that we want to get up online and have people share so that we can easily find these things. So now it gets us into electrical triangle. So as I mentioned before, when there's other than a purely resistive circuit, we have reactive power. And that gets us into the triangle. Things like capacitors, motors, they tend to force the current to either lead or lag the voltage and cross in a 0 point. The more common one is that it's an inductive load, a motor type of load, and that's dragging the amperage back so that it can't quite cross the 0 point at the same time that voltage does. So it's lagging it, and that's what gives us a power factor of less than 1. So power factor is always going to be, it's typically going to be 1 or less. It can go over in some weird cases, but utilities don't like that, so generally we stay under it. So they need to be aware of this, and they need to look at the power triangle to start to understand how to do the calculation for it. So here it's showing that in this case, we got a light on this, right, Larry?
Yeah, press the middle button.
Middle button. So voltage crosses 0 right here. Then a little while later, amperage crosses. So if we're taking a measurement with our tools, voltage is going to give us a high, the peak number it sees, and amperage, you take an amp measure, it's going to give us peak number it sees. But if we take and multiply these two numbers together, they're not occurring at the same time. So we're going to get kind of a false wattage. So we have to add that power factor in. So that's where the power triangle comes in. This is kind of a little bit more of a detailed discussion of that. Here we show it again, but the total paired power, so total paired power is volts times amp divided by 1,000, you get kVAR, kVA, I mean. There's also a discussion on RMS. You know, as I said, peak, but it's not really peak. It's a RMS value that we want to be getting, or an average value. And Fluke has a really good discussion of that on this website, and I'm sure there's other sites that have it too. So you go to that website and just go through what RMS is with your students. So total power is not real power unless it's a purely resistive circuit. So then we have to give them the tools to do that, and that's where you add in a power factor. I don't know, when we were setting up the equipment yesterday, we looked at some of the equipment that we had in the lab, and there's some troubleshooting to go on with some of the power factor on one of the pieces of equipment. And I don't know, Hadley, you going to go through that at all?
Yeah, I'll talk.
He'll talk a little bit about that. And then Mary came in, brought her equipment in, boom, got the right power factor right away. So the other part is the reactive power, and it's called kVAR, and that's volts times amps reactive. And you figure it out by doing this calculation here. You have the power triangle. It's a right triangle. So you have total power is the hypotenuse, and then the other two legs are kVAR and kilowatts. So kilowatts along the x-axis, kVAR along the y-axis. They're related by all the same things that trigonometry tells you for figuring out the length of any side, and you can calculate what they are. Another simple way to do it is just do the cosine of the angle, and you get that too. So I know, Brian, you want me to go through this. Are there other aspects of this that you want to try to point out?
No, we're going to get deep into this.
Okay. All right. I'm probably already too deep into it already. So here's my power factor analogy. You like that, Robert? So,
Spoken like a true Wisconsin.
yeah, exactly. I had some fun this weekend setting this one up. I've had others over the years, but real power is like the beer in your glass, right? Actually, not the beer that you want to drink, the liquid beer. Reactive power is the foam. So I've made beer over the years. I've judged beers at a state fair for a year or two. So I had a little bit of background in beer. And when you're doing that, you start to realize there's all these different flavors and things you want to get out of the beer. Just like we realize there's all these different things we want out of our electricity, like moving motors and capacitance and charge things, stuff like that. So there's all these things that come into play for a glass of beer. But what a lot of people really want out of a glass of beer is that work that it does to get you inebriated, right? And that's what's in the liquid. So when you're drinking your glass of beer, the foam is actually a necessary part of making beer. It's part of the CO2. It's also a necessary part for you to better enjoy your beer drinking experience if you're really into it for the flavor. Because that foam helps to aerate some of the flavors of the beer into your sinuses, which enhances, improves your tasting. So it's a critical part. Just like for us, reactive, that magnetizing current, that magnetizing aspect of electric circuits is really important for making that motor work. So there's a direct analogy to this. And actually, if you go to this website, and that's the one for the engineering mindset, they do a much better job of showing that relationship. They actually do use beer. I found out. It's kind of funny. So, but in that case, so you have total beer, it's a glass of beer, the whole thing on the hypotenuse. Your reactive part's your foam. And your liquid's the thing that does the real power for you. And that's along the x-axis there. So some common electrical signals that we use for controls. 0 to 10 volt DC, 420 milliamp. Control power, we have 24 volt AC, 120 volts. 100 volt amps is the sizing for transformers. So then we get into our discussion about, okay, there's volt amps sizing, making sure we add up all our equipment that's on that transformer, making sure we're not overloading the transformer, things like that. And 24 volt DC. Which ones are I missing on here? I'm sure I'm missing something. Nothing? Well, think about it. You can always add it later. that takes us into monitoring electricity. The project I told you about earlier, I learned a lot about monitoring. And when doing that, you have to kind of decide, why am I monitoring this stuff? What's the really critical nature of this? So if you look at some of the sources online about it, they'll tell you different things. But why you measure it? Well, to determine the load on equipment. So determining load on equipment tends to be more of a spot type of thing, just to see how loaded up that equipment gets. But you're not really using it to compare other things to. You know, you're not using it long term to judge whether a piece of equipment's running okay or anything like that. So that type of measurement doesn't have to be as accurate as other things. Measuring energy consumption. If you're just measuring energy consumption just to do a study of some type, not having one that's performance-based or whatever, accuracy is not necessarily all that important, right? But if you are, accuracy can be important. And that's where you get into looking at your utility metering. You want to monitor for a long use period of time. And you probably want to go with permanent type monitoring in that case. So when I did my project, I looked at it. I was using 9 Dent Elite Pro data loggers to monitor KW, KWH, KVAR, power factor, things like that. Plus I had probably 80 to 90 different current transformers I was using. After one season, I did this over 4 years. After one season, I told my client, said, you know, it's not worth the extra money to set up these Elite Pros on all this equipment every year. I suggest we just go with the CTs, just measuring with CTs and get amperage only. We can take a spot measurement for power factor, and guess what? That pretty much does us good. But this was not a project that we were looking at energy use, a very specific energy use to guarantee something over time. So it wasn't critical that it was exact, just like what Steve was talking about earlier today. It was all relative, so that's all that really mattered. So the amperage is a perfectly fine measurement with a spot measurement of the power factor. But if you get into wattage, it's more difficult to do, it's more expensive to do, but it's more accurate. And that's the key to wattage. But it does cost more money. I was able to save my client quite a bit of money on the monitoring project by taking that out of it. And it didn't have any impact on the quality of the results. So you want to look at short-term versus long-term. Utility metering tends to be very good, very accurate. So if you can, with your control system, tap into a pulse or some information off the utility metering, that's going to be really good. But we don't always have that choice. There's a lot of manufacturers of different types of equipment out there. Dent Elite Pro, Dranitz, and I had bought some Dranitz and used those over the years. Emon, X-Tech has them, Fluke has it, Onset has some, Rush Track, Siemens, Schneider, Square D, and there's a company called TED, the Energy Detective. I had to put that in there right now. And Veris, there's a Veris monitor in the lab. You'll take a look at that. Hadley will be talking about it. I use those. We have them in our building for monitoring the addition energy, electrical use, and I just have not been happy with them. I've never felt comfortable with the readings I was getting. So I think you might find some information on that too from what Hadley's seeing. The prices of these different devices range all over the place. For me to buy the Elite Pros and the connecting the PT part of it and the CTs, I think it was about $3,000 per setup. I had 9 of them. So it adds up quite quickly. I'm sure it's probably, I don't know, Mary, do you know what costs are today?
The Elite Pro is $1,500 and the CTs are about $500.
Yeah. So maybe it's a little less expensive today. So anyway, so that's the different range of prices and different type of manufacturers. I'm sure there's more. Mary will tell us a little bit. Making sure you wire these up correctly is really important because this can screw you up in a heartbeat. And when I was doing it, I didn't have readouts on the equipment. So I had to hook up a laptop and check it, and you're under time constraints. And if you set this up wrong, you come back a month later after you've had your extreme events where you want to really tell your client what's happening, and you messed up the wiring, you're out of luck. So today it's much easier with readouts and things like that. But getting this set up correctly to begin out with is really important. So you got to hook it up, and then use your smarts. And it's things you got to emphasize to your students. You got to make sure things look logical. They can't just walk away and say, "Oh, I'm getting amps, I'm getting volts." They got to actually do some checking to make sure that those numbers actually make sense. Because if they're measuring a phase to ground Y480 circuit, or they think they're measuring that, and they're getting 480, well, they better think twice, right? Should be 277. Mary, you want to come up and talk a little bit about what you're doing? Mary's with PG&E and runs their tool lending library. I know there's various states around the nation that do also have tool lending libraries. Wisconsin used to have one, but they decided to get rid of it back around 2010, and I was lucky recipient of all the equipment they had.
Oh,
So.
cool. Can you hear me? If I don't use the, I need to use the mic, okay. All right, now can you hear me? Much better, thank you. So I'm Mary McDonald. I work at the Pacific Energy Center, which is run by PG&E in San Francisco. We provide a whole lot of free energy efficiency resources. We provide free classes, free technical consultations for your projects, and what I run is the tool lending library. And we have an inventory of over 5,000 tools, over 400 different types of tools. And we loan those to California ratepayers for free, which is nice. So I can take a little bit of the cost factor out of your analysis. Yeah. How many of you are from California? So just a few. And then the rest of you are from out of state. So I don't know if you have a tool lending library. If you're in California, feel free to contact me at pectools@pge.com. And I also have a card for you. Or if you're outside of California, feel free to contact me, and maybe I can help find out if you have similar resources in your state, or help talk to people about how to set up similar resources. We've been doing this for 25 years, and we provide pretty good service, I think. I feel privileged to work there. I do want to disagree with you a little bit. That's okay? Because we really, I was going to go into a little more about our offerings, but I think I'll stay focused on the power and energy a little bit. We have, like I said, the Elite Pros cost about $1,500. The CTs, if you're doing three-phase power, you need 3, and those are going to be $40, $50 each. So you can get one for under $2,000, but our borrowers use anywhere from 3 to 10 to 15 on a project. So you're right, if you have to purchase those, they cost a lot of money. But you can just, if you're in California, you can just go to our website, register as a user, create a project description, reserve and borrow the tools for a month to 3 months, and we've gone up to 6 months in the worst cases, probably. We're doing a study right now about the effect of power factor on energy calculations, because we have a lot of borrowers who want to do that. They want to just monitor one leg of a 3-phase load with an onset logger, which will give them amperage. And then they will do the spot check on the power factor. But we're finding, particularly with the VFDs and some of the other equipment, that power factor is going to change with the load on the motor. And we even have we have 2 single-stage pumps for our system at the PEC, and we found that the power factor will vary based on the load of that pump. So it's got 2 levels that it typically operates at. So I'm in the middle of trying to do some energy calculations to say, well, if you did this with just the amperage and applied it, you'd get this amount, a calculation of energy savings or energy use. If you did it this way, and then if you did it with the true RMS values, you would get, and with the elite logging, you would get this number, just to show what the amplitude of difference is in those numbers. Because actually the three-phase law, or the true RMS loggers, and you'll see I have an Elite Pro over there that's not set up, but I'd be happy to show it to you. It does not have a display, but you'll also be using the Summit Technology power site meter, and it does have a display, and it's really good for troubleshooting. The power site, you can just launch right with the keypad. Or you can use Power Site Manager, which is very intuitive, and you can launch it for logging. The Elite Pro, the software is just as simple as what you would use for the Onset or some of these other loggers. And the Elite Pro has a really nice system where they have things called phase check lights, and these lights are all green if you've got it hooked up right, but they're red and blue if you don't, and so you know you have to check something and change something to get it set up right.
You know, and I didn't hear anything about this agreement though, really.
The what?
The disagreement part.
I was just saying I prefer to use the true RMS meters and not, yeah.
Definitely. I don't disagree with that at all. It's just that, you know, for what we had to do, it just, the accuracy need wasn't there.
Well, and then there's the other thing is once you get an idea of your load profiles, you also did that after you had been doing a number of the
Yep, that's
studies,
true.
and you knew how
I had-
certain
I had to
factors
break it down that
varied.
way.
And so you could use that, and that is a time. Some of our borrowers will do the true RMS on one load, and then on the other similar loads, they'll just monitor the amperage. So there's validity to both. Anyway, so that's, besides that, most of you don't even live here, so you don't really need to know how to borrow from us. But I look forward to looking at the power loggers with you over there and seeing how they work. I'm going to be learning from these guys too a little bit.
All right, I'll take the mic from you.
Oh, that would be nice. There's that.
All right, so I'm just going to talk into this. It's about that time for Hadley and Chuck to come up and talk as I kind of close out my presentation here. The last thing that has been an issue that I've seen in my labs, and I know a lot of us have talked about it, is what do you do with PPE equipment, safety type of issues in your labs? Where did Bob go? That's right, that's right. Well, NFPA 70E has these requirements. So this is just their kind of base requirement for protection if you're going to go into an electrical panel of any type. And you can see that they have these arc ratings of 4 calorie per centimeter squared, and you have to be wearing long sleeve shirt. Probably it can't be any type of polyester or anything like that, because that'll just shrink right on you and burn your skin. It has to have fire rating to it. You should be wearing a face shield, hard hat, safety glasses, hearing protection, heavy-duty leather gloves, leather footwear, a lot of equipment just for going into panels. And how many of us actually do that? Well, you know, it's hard to get students to do these things, let alone ourselves. So it's something that I think as a group we need to talk about more and start seeing how other people are addressing it and working with it. So another thing I'd like to get up on our website is some discussion about policies that you have. Maybe just put up a sheet or two of policies that you follow at your school and see if we can try to interact and get more information up there on that. It's something that's important. I think we need to, because we need to be setting an example for our students. So it's something that's really critical to do. If we're not doing it, they're not paying attention. It's just like with our kids, you know. We model the behavior, we need to model the behavior that we want them to have. And so safety equipment is one of those areas that we really need to make sure that we do, at least for me, a better job of doing it.